So going over the homework from last day, number 8, I see a change in direction. They're asking average force. I think this is, although this is, you could argue it's a collision between a ball and a wall, I think this is a job for impulse, for change in momentum. I think what I want to do is this. Impulse equals change in momentum. Because they're interchangeable. But Petra, I think what I'll say then is this is going to be final minus initial. Final minus initial, except what is momentum? What times what? Okay, so this is going to be, I think what I'm really going to get is this. Force change in time equals mass v final add a vector, remind myself direction is important, minus mass v initial add a vector, remind myself direction is important. What did you say this was asking me to find? You know what? I'm actually even going to do this. D over t, except I apparently need to erase that little thingy there. By the way, what I've really written is this is the equation that Sir Isaac Newton gave us for Newton's second law. This is ma, except instead of a, I wrote change in velocity over time. This was the way he phrased Newton's second law back in the day. We just say F equals ma, but he was much more interested in impulse momentum. Okay. So I would say something like this. Mass, 75 marbles per minute. So I guess the mass is going to be 75 marbles times 0.035 grams, and I guess my time is going to be 1 minute, which is 60 seconds. V final, 3 minus mass, 75 times 0.035. V initial, oh, please be careful. Don't say 7. What? -7. Did you do this, Michael? Because maybe my answer key is wrong. Or, oh, there is an answer.
I was just confused by how it was saying a 1 second interval and how it was giving like an average rate of.
Okay. So you know why it said averaged over a 1 second interval? That's why I'm dividing by 60, because I'm dividing by 60 seconds. That's going to give me the force for averaged over a 1 second interval. Is that all right?
Yeah.
And now I think crunch the numbers and you should be there. Okay. The other version I've seen, instead of bouncing a ball off of the floor, tilt this vertically, have a car hitting a wall and bouncing off a wall. And the reason I like this question, Nathan, is the most common mistake I see. Kids put in a 3 and they put in a 7, which is wrong. 1 better be negative, because there is a change in direction. Kids miss the change in direction. Is that okay? Any others from the homework? Yeah. Number 7. Staying on this page. Okay. This is from last unit, but hey, good review. What are they asking you to find? What are they asking you to find? You know what? I see this. I see a force versus distance graph. You know what? I think I'm going to be saying that. Is that okay? Plus change in potential, but I don't see a change in height mentioned in the question, so I'm making the assumption that the change in potential is 0. I'm using the work energy theorem, except look up, look up, look up, look up. Right? Because work could be force times distance, and it could be, howdy, give me 1 second, kind sir. Hang on, let me pause the recording. That's my also way of, okay, we're back. Okay so far?
Yeah, well, I was just trying to solve the convention, that's why I didn't know.
Nope. I don't think so. The reason is I don't see a constant force, and I think, again, in our impulse equation, we're assuming either constant or it's actually an average force that you're using. Hey, if it's a straight line, I can find an average force because it's probably add the top and the bottom and divide by 2. But when you got a straight line and then leveling out, the average force is much tricky. Yeah, whatever. So yeah, and then you can find the area. It's going to be a triangle plus a rectangle. That's going to go here. And this is going to be a half mv squared final at rest, so no v initial. So it's going to be divided by a half m square root, and away you go. Okay. Yeah?
I think
You think my answer might be wrong? Let me double check it. 75 marbles per minute, which means it's going to be 60 seconds. 35 grams is 0.035. They're moving downwards. I better let that be negative. Let's bring up my calculator and see. I'm fairly good with my method here, I think. So bracket 75 times 0.035 times 3 minus 75 times 0.035 times -7. Close off the top, divided by 60. Oh! Now, how come when I go like this? Nope, that's not it either. Did I change the numbers on this question? Let me pause things for a second here. Any others? Going once, going twice. So if you have lesson 5 done, could you please hand that in? Lesson 6, two-dimensional momentum. You may recall in the forces unit, when we went at an angle, I said something like, hey, this is when physics 12 actually starts. Hey, this is when physics 12 momentum actually starts. Because the last lesson, lesson 5, was actually a review of physics 11. Just me, again, Petra, making sure it was fresh in your brain and that I dotted my I's and crossed my T's. We're going to start off, though, with something that's in a nice straight line and show you how we can combine in some questions momentum and energy. Let's shoot a bullet into a block. It says this: a 30-gram bullet moving at 250 meters per second strikes a 5-kilogram wood block at rest. You know what? Probably I would choose to underline the word at rest. I'm guessing that's important. And sticks into it. If the bullet and block move off together after the collision on a frictionless surface, A, write a momentum equation. B, find the speed of the block after impact. And C, find the heat energy created during the collision. Looking at this, I didn't leave you anywhere near enough room, which means write small. I'm actually going to show some of my work over here, some of my work over here, and some of my work down here. See the bullet? See the block? See the picture? Is there a collision? This is a job for? No, not change in momentum. No, impulse.
No, conservation.
Conservation of momentum. So collision is conservation of momentum. In other words, Cliff, as soon as I see a collision, I'll read it still, but almost always my first instinct, my first inclination is going to be to write something like this. The sum of all the momentum before the collision, that's an initial, equals the sum of all the momentum after the collision. Put vector bars on both of them. And if you wanted to, you could argue that that's the momentum equation for part A. Except, I'm going to break it down a bit further. Before the collision, what's moving? The block, the bullet, or both? You know what? I got a bit of a problem. I would normally go MB for block and MB for bullet, but the fact that they both begin with a B, how about since the bullet appears first, that'll be mass number 1, and we'll call the block mass number 2. That's okay? So before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. So it's going to be momentum of 1 initial. Wham! They collide. After the collision, I love this unit. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Momentum. Both. Final. And now, from now on, you're going to stop and you're going to read the question and you're going to say, hey, are there angles? Is there a north of south, east of west? Is there a picture that has like something banking off somebody? Any angles anywhere? No, but you're going to have to ask that every time, because if the answer is yes, you'll find, oh, my strategy changes. I start dulping. I start drawing vector pictures instead of going straight to doing arithmetic and equations. But I'll ask that question here. Hey, are there angles? Do you see any thetas? Do you see any north of south, east of west, anything like that? No. So we can relax. We'll let one direction to the right, I think, be positive, and we'll let the other direction to the left be negative. So far, so good? So This is going to be mass 1 V1 initial equals M1 plus M2 V final. You okay with that, Kelly? You could argue that that's really the answer for part A. When it says write a momentum equation there, I've kind of plugged everything in. Kelly, what does B want me to find? Hey, what's that in my equation? How would I get the V final by itself? Okay, I think I can do that here. You know what? I'm going to do that over here. B. V final is going to be M1 V1 initial all divided by M1 plus M2. V final is going to be, what's mass 1? Don't say 30. Yeah, 30 kilogram bullet would be called a cannon, right? Yeah, so 0.03. V1, 250. I'm good with that. The units are happy. All over. Can you add mass 1 and mass 2 together in your head, please? 5.03, yeah? What do you get? 0.03 times 250 divided by 5.03. 1.49? Almost 1.5, not quite. 1.49 meters per second. By the way, if you knew the speed they moved off at, could you work your way backwards and find how fast the bullet was traveling? In other words, Nate, look at equation A. If I knew V final, could I find V initial? And this is starting to lead you to what we used to call the ballistic pendulum. I don't know if you ever wondered, back before radar and computer timers were invented, how the heck did they figure out how fast bullets were traveling? It's not like you could time it with a stopwatch. Humans can't react that fast. What they would do is they would use something called the ballistic pendulum. They would fire a bullet, bang, into a block of wood hanging from a string. And they would measure how high the block of wood and the bullet swung, because energy is conserved even though it was a curvy path. And if you knew the height, you knew its gain in potential energy, which must have been its gain in kinetic energy, which meant you knew how fast the block moved after the collision, which meant you now knew V final, and you could find how fast the bullet was traveling. This is how they did ballistics, probably until about 1950, 60-ish. You did it mathematically in an experiment with cameras and film and observation. Because you certainly couldn't figure out how fast a bullet was traveling with a stopwatch. We'll actually look at that. It's a little old school, but we'll look at that a couple lessons from now. It's called the ballistic pendulum. It's a nice application or combination of both momentum and energy. It's got a collision, woohoo, and it's got a curvy path, change in height, change in speed, woohoo! How much more can you ask for, right? We okay? V at 1.49? Peter, what's C asking me to find? Wait a minute, Peter, you're an elf. I got to leave you alone. Petra, what's C asking me to find? The heat energy created during the collision. I think what we're going to say is, let's find out how much energy there was before the collision, how much energy there was after the collision, and whatever's missing must have gone into heat. Is that okay? In other words, I think C is saying this is a job for conservation of energy. Now, there wasn't a change in height, change in speed, curvy path. Well, there is a change in speed. There wasn't a change in height, curvy path, but Ray, since they said heat, that's my natural inclination. Did I say there wasn't a change in height? Well, then, hey, what can I cross out, Ray? Oh, never mind, I can't go to you, you're an elf. Ashley, what can I cross out? If there's no change in height? Yes? And? Yes? Okay. Petra, what did you say they're asking me to find here? Oh, how would I get the heat by itself, people? Don't say divide! How would I get the heat by it? And by the way, sure enough, one person did do that on the test. Oh, he was, because that's his best test, and for him to do that, he was like, jeez. Anyways, subtract. So I think we're going to get this. The heat is going to be KE initial minus KE final. You're done? Fine. The heat, which I'll do in red because it's heat, haha, is going to be a half m v initial squared. Now careful, 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 careful. Before the collision, which mass? Before the collision, which mass? This is going to be mass 1 minus, now the final kinetic energy, which mass? Okay, a half m both v final squared. Have I gone over the work and energy test yet? I don't think I have I? Well, I do have a special message for someone in this class. Harjo, can you read to me this equation right here? Sorry, V what? Sorry, V what? V what? V initial what? V initial what? Guess what you forgot to do 3 times on the test. V initial what? Squared? Okay, good. I damaged your self-esteem. I apologize, but I couldn't let you do that mistake again because you did. You'll find that I wrote you. Wait till you get your test back. I wrote you lovely notes. I think I even did a little hangman game for you with like the clue is square. Anyway, you'll okay. Sorry, but it's so important that I lovingly beat that out of you. So okay, I did that. Leave her alone. 0.5. Claire, what was mass 1? It's the bullet. Thank you. I should have. You know what? I should have waited a little longer. That was my fault. Hey, Claire, what was V1 or V initial? Squared. Squared? Did you say? Oh, good. Minus a half. Now it's mass of both. 5.03. 1.49 squared. I think I can fit it right here. I hope you get a positive answer. I think we did lose some to heat. .5 times 0.03 times 250 squared minus 0.5 times 5.03 times, I think that answer was still there, squared. Do you get 932 joules? Yeah. What are we saying? Momentum, this is why momentum is so much nicer to analyze collisions. Momentum is conserved, total energy is conserved, but kinetic certainly is not, and kinetic and potential certainly are not. Some energy must have gone into heat, otherwise this couldn't be possible. Example 2. Is that okay? The diagram below shows 2 pop cans of unequal mass initially at rest. That's probably important. Again, you don't have to underline the physics work, but Race, it's a good strategy, at least in your mind. They should be almost like highlighted in separate color. At rest, that's a key one. Stopped is a key one. You know, stuff like that. An explosive charge is detonated between them. Boom! And the cans fly apart. What can you say about their velocities after the explosion using principles of physics? Explain your answer. So if I have one can of mass m, and how big is the other can? 2m. Okay. What could you tell me about their velocities? I'll give you a hint. Opposite directions. So one's positive and one's... Can we be more specific than that? Yeah.
M has twice the velocity.
The lighter can, mass m, going twice as fast? I agree. Prove it.
The initial.
So hang on, let's write this down. M will have twice, that's a will, there we go. By the way, I take issue with the word velocity because they're in opposite directions. What word should you have used? Speed. Jake, is there an explosion? Yes? Is there a jeune? You know what this is a job for? The sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what's moving? Mass 1, mass 2, or both? It's a trick question. None. Oh, so before the collision, what's the momentum? So after the collision, I better be able to, okay, 0. Wham! They blow up. I guess I'm going to have, boy, that was a weird pen glitch there. Let's try that again. Let's call this mass 1. Let's call this mass 2 since the 2m has a 2 in front of it conveniently. I guess it's going to be momentum 1 final and momentum 2 final. Or, you know what? I think I could just rewrite this as momentum 1 final is going to be the opposite, negative, momentum 2 final if I minus the momentum 2 over to the other side. Yes? Talk to me, Jake. What's your next argument? We're doing an algebraic proof, and I think you were going to give me the same proof in English, but I'm trying to walk you through the algebra. What might you do now? How about what's momentum? Oh, so if I hear you correctly, and I think I just did, you're saying this is going to be mass 1 V1 equals, there's a negative. Oh, what's mass 2? 2m. Let's call that V2. I guess that's 2 mass 1s. Is there a mass 1 on the left? Is there a mass 1 on the right? Is there mass in everything? Well, then what can we say about the masses? Let's rewrite this. You're saying the first velocity is twice the second velocity, but in the opposite direction. That's what you said in English. There's a lovely proof with no English for my ESL students or for my nerds, either or. Is that okay? Okay. Yeah. They blow apart, but the lighter one goes twice as fast. And I've done this one. I could have, by the way, Ashley, made up reasonable numbers. You could have said, I'll let mass 1 be 2 kilograms, mass 2 be 4 kilograms. You could actually have found the speeds. But I've done a lovely algebraic proof. Some terminology. I'm going to use these words in questions. The first is when the masses stick together. We call that an inelastic collision. An inelastic collision, or when they collide inelastically, it means the cars stuck together, the wreckage stuck together, the bullet stuck inside whatever it hit, the masses stuck together. And momentum is conserved, but for what it's worth, this is when you lose the most kinetic energy because lots of energy goes into bringing the mass that's stuck together to a stop. For example, in the ballistic pendulum, the bullet that we just did, Yes, they moved off together, but that bullet lost almost all of its kinetic energy. It had to go somewhere. Oh yeah, it went into heat. Okay. The second, you can scratch out the word partly. We're just going to call it an elastic collision. In an elastic collision, they bounce off each other. Body checking. Some car crashes. Curling is a great example because curling rocks don't stick together. They bounce off each other. You need to know the difference between an elastic and an inelastic collision. And there's an easy way to do that. This is what kids have been doing for decades and decades. Whenever I see the word elastic, I think rubber band bounce, they bounce apart. Inelastic, I think not elastic. Elastic, rubber band, rubber, bounce apart. Oh, inelastic, don't bounce apart. So if you're looking for a dumb way to keep them straight, because that's going to, Claire, totally change how you write your momentum equation. If I say it's inelastic, then it's going to be equal to momentum both stuck together. If I say it's elastic, it's going to be momentum 1 final plus momentum 2 final. Right? You okay? Then there's a and also you'll notice momentum is conserved in the first one, momentum is conserved in the second one, momentum is conserved in the third one, the one that I'm about to look at. In other words, Alex, momentum always conserved. What about energy? Kinetic energy, I mean. No, not conserved. You lose a bunch. Still not conserved. You lose some. Then there's something magical called a perfectly elastic collision. The mass, it's elastic, so the masses bounce off each other. But it turns out your kinetic energy is conserved. And I'm going to give you a couple of more things about a perfectly elastic. And this one you want to file in your back pocket. There's going to be a question you're going to see in the future when I tell you a collision is perfectly elastic. And you're going to freak because I didn't give you much information. But the reason is, if you know a perfectly elastic collision, Hakeem, you know a bunch of other things. First of all, you know they both have the same mass. I'm going to give you a perfectly elastic collision. I'm going to give you mass 1. I won't tell you mass 2. I don't need to. They're the same mass. I'm going to tell you they bounce off at an angle, but I'm not going to tell you the angle. It turns out in a perfectly elastic collision, the angle they bounce off at is 90 degrees. I won't tell you that. So, if you know the collision is perfectly elastic, you know the angle is 90 degrees, you know the masses are identical, and it turns out the law of conservation of energy pops out of there. Kinetic energy is conserved. When does that happen? In real life? On the macro world? Never. On the atomic world, when particles collide into each other? Fairly often. There is no loss of kinetic energy there. But we'll occasionally make up one in our magic physics world on the macro scale. We'll occasionally have curling rocks be perfectly inelastic because they have the same mass. And big deal. Example 3. Read it. I'll read it out loud with you. A 60-kilogram hockey player traveling 2 meters per second toward the north collides with a 50-kilogram hockey player traveling 1 meter per second towards the west. The two become tangled together. With what velocity will they move after the what? After the what? After the what? This is a job for conservation of momentum. The first thing I'm going to do is this. This is not going to change. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. But from now on, I'm going to pause either here or on the next line. I'm going to say, hey, is this question giving me directions or angles or thetas? Is it? Yeah? Then I'm also going to draw a compass rose somewhere off in the margin because the number of times I've got this wrong would amaze you. I'm going to continue on as before for a couple of more steps, and then, Neve, we're going to change. So, hey, what was the next thing I asked myself after writing this down? Do you remember? I said, before the collision, what did I ask? Before the collision, what's moving? Mass 1, mass 2, or both? Before the collision, what's moving? Mass 1, mass 2, or both? Race. Stuck together or separate before the collision? So I'm going to go like this. Momentum 1, initial plus momentum 2 initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Both, stuck together or separate? What's the fancy word for stuck together? Inelastic, okay? I'm going to start to use that. In other words, you'll start to see questions in a couple of days where I don't tell you they're stuck together. I just say they collide inelastically and move off. That's the fancy speak for they stuck together and moved off. Jordan, have I done anything different from before? Not yet. Now I will. This is the line where I pause and I say, hey, are there angles? Are there directions? Are there angles? Are there directions in this question? What does DOLP stand for? Draw a little picture. Jordan, my friend, can you read to me the sentence that describes the first mass, the first hockey player before?
60 kilogram hockey player traveling at 2 meters per second toward the north.
Toward the what? So I'm going to draw underneath momentum 1, little vector sign pointing to the north, and I can even tell you what number goes on it. Momentum is what times what? Momentum is what times what? What was his mass? What was his velocity? Michael, really? You reached for a calculator? It's 60 times 2. It's 120. But it's 120 north. Units, kilogram meters per second, but okay. Plus Alex, can you read to me the description of the second hockey player before?
50 collides with 50 kilogram player traveling 1 meter per second towards the west.
Toward the what?
West.
So I'm going to draw an arrow like this. Michael, in your head, without a calculator, can you multiply his mass times his velocity and tell me what number is going to go on that arrow?
50.
Thank you, Michael. You guys. Have they told me anything about the final, like in terms of direction or given me any hints? No. Wait a minute. I have 2 vectors with an addition sign between them. How would I add those 2 vectors together, oh pray tell? Oh, now you know why Mr. Kamosi and I pounded that in your skulls last year and myself this year. We're going to draw them tip to tail. So it's going to look like this. 120. And now I'm trying to be a bit more accurate in my scale. I figure 50 is a little less than half of 120. Yes? What's the resultant from the tail of the first to the tip of the second? There's a picture of momentum both final. It's time for some trig, Curtis. Is there a right angle here? Oh, thank God. There will rarely be a right angle. Most of the time, you're going to be pulling out the cosine law and the sine law, and we're going to get good at it. But for now, we're easing you into the shallow end. How could I find the magnitude of the momentum? Thanks, kiddo. Bring it up. Put it on my desk right here, okay? How could I find the magnitude of the momentum? Pythagoras, holy smokes, let's do that. So I'm going to write down here momentum both final is going to be, it's going to be 50 squared plus 120 squared square root. I think this will actually work out evenly. I was trying to cook the numbers a little bit. Yeah, just right there is fine. It should be 130. You can use a calculator for this one if you want to, Michael. But I think it's the 5, 12, 13 triangle in disguise with zeros. Yeah? Except that's not what they wanted me to find. What did they want me to find? Velocity. If I know a momentum, how can I find a velocity? Divide by mass. I think in this case, mass of both because they stuck together. By the way, hopefully you're seeing why I did that routine every time. Stuck together, separate. Mass 1, mass 2. I'm trying to give you, these are the questions, Petra, that you ask yourself step by step by step by step, except now we add some trig. Okay? So if I want to find V final, that's going to be 130 divided by M1 and M2. That's going to be 130 divided by mass 160, mass 250, 110. You can use a calculator for this one too if you want to, Michael. What is 130 divided by 110? Sorry? 1.2 even? Give it to me to 3 sig figs. 1 point, so 1.18? Hakeem, what did you say this question wanted me to find? I found the speed. How do I turn that into a velocity? Oh, let's go back to my triangle. I think the direction is going to be, yoink, that there, where it comes from, right? We always put the theta where our resultant originates. By the way, that angle, what of what? North of south, east of west? What of what? It's going to be west of north. I just got to figure out how many degrees. Which trig function can I use? Tan? Opposite? Adjacent? You're right. Tan theta equals opposite over adjacent. Shift tan of that, what do you get? Oh, and you can use a calculator for that too, Michael. Sorry. I'm in a snarky mood today. Poor hard joke, poor Michael. 22.6 or 20, I'll go 22.6. 23 is also fine. Before you turn the page, here's the problem, Nate. I would say about 1/3 of my students, when I give this to them on the written, you're probably going to get 3 of these on the written of your test. They don't notice the angles, and they do it purely as though everything is in a nice straight line. In other words, they add the 120 and the 50, and they divide by the mass, and they just tell me, oh, that's it. They don't add them vectorially, they just add the numbers. And unfortunately, I usually cap that at 2 out of 7. Because I give usually 1 mark for this, 1 mark for that, and then 1 mark for the vector triangle, 1 mark, 1 mark. I give out, all my marks are later on. In other words, start asking yourself from now on, if there is a collision or an explosion, are there angles? If there are, trig. Turn the page. I think I left you the whole half page for this one, yes? Okay. Hey, look at the picture. Is there a collision? Yeah. Look at the picture. Are there angles? Yeah. Look at the picture. Are they nice right SOHCAHTOA angles? Nope. Okay. Oh, and then there's a part B talking about kinetic energy. Actually, the energy part is nicer because energy is a scalar, no trig. But getting the numbers, whew. Did I say there's a collision? You know what this is a job for? Okay. What are they asking me to find, Bree, in part A? I'm going to actually find the final momentum and then divide by the mass. Same trick as we did before. Okay. You said there's angles and stuff. Now there's a collision, so step 1 hasn't changed at all. Step 1 is still the sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what's moving? Mass 1, mass 2, or both? So I'm going to write momentum 1 initial. Thank you, sir. I should have done it while he was here. Wham! They collide. Missed out on an opportunity. After the collision, what's moving? Mass 1, mass 2, or both? Inelastic or elastic? Elastic, bounced off, not stuck together. Okay? So it's going to look like this. Momentum 1 final plus momentum 2 final. And I'm leaving some spaces. I want room so I can dulp. Are there angles? We stop. We don't start plugging in numbers. We have to draw pictures. Looking at mass 1 initial, oh, it's moving nice and sideways. I can draw that. It would look like this. Right? And I can even tell you how big it is without a calculator. What's the momentum before the collision of mass 1? Momentum is mass times velocity. The mass is 2. The velocity is 8. Michael, in your head?
Sorry.
In your head, the initial momentum?
16.
Thank you for recovering. I'll leave you alone for a while. No, I won't. Anyway, I'll try and leave you alone. Wham, they collide. Now, looking at the picture there, it looks like mass 1 goes down that way, right? At an angle of about 10 degrees. Oh, and I can even tell you how long that line is. What's its mass times its velocity? 2 times 6.7. Did you do that in your head too? Woohoo! That little Santa's cap. You maybe give it to Mike. Okay. 13.4 plus. Do I know the mass times velocity of the 10 kilogram mass after the collision? I know its mass. Do I know its velocity? So do I know its momentum? But I can draw it. Momentum of object 2 final. With me so far? Hey, do you see on one side, Claire, I have 2 vectors? How do I add those 2 together? Why, I draw them tip to tail. Now, here's the nice thing. I also know what they're supposed to add to. They're supposed to add to that 16 there. Yes? So watch. Put your pencils down. Look up. Here's momentum 1. 13.4 at an angle of 10 degrees. Tip to tail. Tell me when to stop. How do I know to stop right there? Because it looks like when I add momentum 2, that 16 is supposed to be exactly horizontal. That's how I knew, Ashley, don't go further, don't go way over here, don't stop right there. I could say, I actually know. You'll always know 2 of the 3 vectors in your triangle. Sometimes you'll know the resultant and you won't know one of the sides like this. Sometimes, like in the previous, you'll know both of the initials and you're finding the resultant. SOHCAHTOA? No. Psst. Is this a sine law question? Well, let's see. If it was a sine law, I would have a pair. Do I have both of those? Nope, I got the 10 degrees, but I don't know that. Do I have both of those? Nope, I got the 16, but I don't have theta. Do I have both of those? Nope, I got the 13.4, so I don't but I don't have theta. It's the job for cosine law. What's the cosine law? Again, it is on your formula sheet, but it's sort of Pythagoras in disguise. It's going to look like this. It's going to be momentum 2 final squared equals side squared plus side squared minus 2 side cos. Side squared plus side squared minus 2 side cos. And this is where the cosine law really shines. This can be done with components. I really want to encourage you, master the sine and cosine laws. Because to do this with components is going to be about 8 or 9 lines. To do this with the cosine law, 2. Because you can already go to your calculator right now. You can already say to yourself, hey, 16 squared plus 13.4 squared minus 2 times 16 times 13.4 times cosine 10. What do I have to remember to do? Okay, this gave me the momentum squared. So don't forget to square root. The final momentum of object 2 is 3.6434. You know what? I'll carry a few extra sig figs. Momentum of object 2 final is 3.6434. Of course, that's not what they wanted me to find. Bree, what did this question ask me to find in part A? Hey, you answered this before. If I know the momentum, how the heck can I turn that into a velocity? Which mass? 2. That's why I'm so careful with my labeling now, yes? Michael, how big is mass 2?
Mass 2 is 10.
Do I need a calculator to divide by 10? Or might that be something I could perhaps do in my head? Let's find out. Okay, so velocity of object 2 final is going to be 3. Let's write it in our notes, though, so we know what the heck we did. Divided by, I'll put mass 2 there, and you guys will clue in that that's a 10. So the final speed is 0.364 meters per second. But that's the final speed. Bree, what did you tell me this question was wanting me to find? Not speed, but what? How do I find a velocity? I'm going to need an at. Okay. Look up. I'm going to zoom in on this diagram here. I hope I can. Maybe I can even zoom in a bit more. There we go. What I really want, I think, is this angle right there. First of all, that's where I always go back race to where it's originating from. But the reason I don't want this one is it's not north or south or east of west of anything. It's angle and angle. I can't do anything with that. So I want to find this one, which is going to be what of what? North of south, east of west, what of what? North of, you know what, Mr. Dueck? You forgot to do a little compass rose, didn't you? Yes, I did. So let's do that right now. North, east, south, west. Should have done that right away, Mr. Dueck. Let's go back here. I think it's going to be north of east. Now, here's the problem. Is that angle in my triangle? No. However, have we used this Z thing occasionally before? Yep. Which angle is the same as that one? This little guy up here. So I'm going to find that. I'm going to make a little note. This is also angle theta. And I'm going to leave a little space here, and I'm going to say it's north of east, just so I don't accidentally write down the wrong direction component. Okay. How can I find angle theta? SOHCAHTOA? No. Well, I just used the cosine law. You know what? Once you use the cosine law, you know how you can almost always find an angle? Sine law. Because you will just have generated a pair. I didn't have a pair before, but now I know what this 10 goes with. This 10 goes with 3.6434. In fact, it goes with 3.64340987. That bad boy. So, I can go like this. The sine of theta over what's across from it, 13.4, equals the sine of 10 over what's across from it, 3.6434. This is the other reason I carried a few extra sig figs. I knew I was going to be using that momentum twice. So far, so good? Whew. Oh, I can move that 13.4 up there. And then it's going to be, I think, shift sine of that. I think it's going to be 13.4 times the sine of 10 divided by, conveniently, I still have this number in my answer feature, so I'll use that. What? Oh, shift sine of that. Second function, sine of that. And I'm getting 39.7 degrees. 39.7 degrees. Part B wants us to do stuff with like the kinetic energy. We are going to pause here. But before we zone out, again, key ideas here, Peter. Collision, explosion, still conservation momentum. But if you see them talking about angles or directions, once you figure out, hey, before the collision, what's moving, mass 1, mass 2, both stuck together or not, after the collision, then DULP. Don't start going M1, V1. You'll be too tempted to start to do the arithmetic, and you can't. You have to draw a little picture. And you can put the mass times velocity on your picture with the correct directional component. Is that okay? No. We need to practice this way more, which is the other reason I'm pausing now. So there's 15 minutes left. You have both a take-home quiz, and most of you have the homework from the last lesson as well. I'm going to shut up.